I kind of, as I was leafing through the test, I was like, "Oh, this looks like a resistor. These look like the color codes on a resistor, but it's not. It's a spectral. These are spectral lines here." Okay. The diagram shows the position of the principal lines in the visible spectrum of the atomic hydrogen and some of the corresponding energy levels of the hydrogen atom. Okay, let's see, atomic hydrogen. The hydrogen atom, all right, there we go. All right, so notice that this, by the way, is in 10 to the minus 19th joules as opposed to electron volts. It took me a little while to figure that out, right? Determine the energy of a photon of blue light emitted in the hydrogen spectrum. Now, the mystery to me is like, why is that worth 3 marks, right? You're just going to do E is hc over lambda. And I just went ahead and used the hc that's in the front of the data packet. Determine the energy of a... And I figured it out in joules. And the reason I did it in joules was that this is in joules there, right? Okay. And you'll get something that is between 4 and 5 times 10 to the minus 19th joules. Okay. Okay. Then it says identify with an arrow labeled B on the diagram the transition in the hydrogen spectrum that gives rise to this. Okay. So what you're looking for is whatever that answer is there, right? It might be 4.5747 times 10 to the minus 19th joules, right? Okay. When you find that value, you're looking for some difference here that equals that, right? And this is, of course, what your explanation is, right? Is that the energy, it's going to be a downward transition. So, does this work? Does 0.87 to here, does that work? Right? Well, no, that's not big enough, right? Does this work? Can I go from here to here? Does that work? So find the difference between that. Does that equal this, right? It's kind of like, are you my mom? So find some transition there. And it's got to be equal to this, whatever that is, right? Keep in mind that that's in joules and not electron volts, as we're sort of used to doing, right? All right. Now, when I flip the page here, this is going to start to go downhill. It's like, oh, suddenly they change this into a diffraction grading problem, but we can deal with this. Okay, low pressure hydrogen discharge lamp contains a small amount of deuterium gas in addition to the hydrogen gas. The deuterium spectrum contains a red line with a wavelength very close to that of a hydrogen red line. That interesting is like an extra neutron. Deuterium, hydrogen is just proton and electron, right? Okay, deuterium would be proton, neutron with an electron, right? And it changes the wavelength just slightly, and I don't know why, but they're telling us that it does, right? Okay, so let's see. The discharge from the lamp is normally incident on a diffraction grating. This is, by the way, we used a diffraction grating. That's what those things were, those tubes were that we put up to our eyes to look at the diffraction gratings. So we have firsthand experience on this, right? The light illuminates a width of 3.5 millimeters. So that's 3.5 times 10 to the minus third meters. The deuterium and hydrogen red lines can just be resolved. They can just barely be resolved in the second order spectrum of the diffraction. What in the heck are they talking about? It's this formula. This is what they're talking about, right? So resolvency is the wavelength divided by the change in wavelength, right? Let me find that in the data packet. It's the ability to, so when you see these spectral lines, right? These spectral lines have some width to them, right? But the more lines you have in your diffraction grating, the more of those things you have, the crisper these lines are, right? And so these things are just barely, let's see, the red lines, these guys here, right? Okay, these can be just barely resolved by this diffraction grating. Now, if you had a cheaper diffraction grating with fewer lines on it, right, then it would be, they'd blur together. You couldn't resolve them. Okay, that's what they're talking about here. Okay, and now this formula is in the packet. And we looked at it last year in those videos. We didn't have a test on it, but This year I'm hoping to have a test on it. Let's see if I can find it. No, I can't remember what section. It's like one of the wave topics, right? Okay. Oh, not there. Oscillations, wave behavior. Okay, electric fields. Resolution, there it is. I resolve. It is additional higher level. It's page 9. This thing is on page 9, on section 9.4, resolution. Okay, it's got the Rayleigh Criterion there, and then it's also got the resolvency of a diffraction grating, right? Okay, so this is the wavelength. This is the difference in wavelength you're trying to find, and that equals the order. This is the order. Now, if you recall, order is, remember when we saw these diffraction patterns, right? We saw the central line, and then we saw a bunch of lines out here, then we saw a bunch of lines out here, and a bunch of lines out here. This is the first order, second, third, right? If you looked off to the side, you see a succession of those lines, right? So that is the order, and then it's N is the number of slits, okay? So what we're going to do here is we're going to figure out how many slits we have to illuminate, right? And we want they want to know what the diffraction, what the grating spacing is, right? So what we're going to do ultimately, that diffraction, the spacing between these things, right, is going to equal 3.5 times 10 to the minus third meters, right? Which is how much is illuminated divided by the number of slits, right? We just have to figure out the number of slits. Okay. So for the wavelength, it really doesn't matter whether you average these, right? Okay, but for the to put in for that wavelength, technically speaking, we should average those two, right? Of this and this. Okay, so average those. I got something like 656.1975. Okay, and plug that in for that, right? And then for the difference in wavelength, it'll of course be the difference between that. I got like 0.181 nanometers, right? 0.181 nanometers. And I got that by subtracting those. So this minus this is that, right? So average those two things, put that there, right? Put the difference between them as the difference in wavelength, right? They say it's the second order spectrum. So put a 2 in for that. And when you solve for the slits, you'll get something that's approximately equal to 1,812.7 slits or something like that. Okay. So you'll get roughly that many slits. Put that number down here, right? So it's on the order of about 1,800 slits. But it was a little more precise. Put that number in there, and you'll get that the spacing, I got like 1.93 times 10 to the minus 6th, which is on the order of 2 times 10 to the minus 6th, right? And that's what you pay if you buy a diffraction grating. That's what you're paying money for, is having these lines, lots of lines, right? That's pretty amazing, right? You'd have to look at this with a microscope to see microns, right? Anyway, so that's that one. Now let's see what the next page offers up, right? Calculate the angle between the first order red light in the spectrum and the second order violet light in the hydrogen spectrum, right? Okay, so where's that formula for that? Here it is. So we're going to use this guy, right? And this is page 9. This is interference, right? So n lambda equals d sine theta. Okay, the d is what we calculated from the previous part, right? Okay, so the d is the thing that we got from bi, right? Which I got about 1.93 times 10 to the minus 6th, right? Now, it's unclear to me whether they want us to use that or their 2 times 10 to the minus 6th meters, okay? I just don't know. They're so conflicted about that. But I used my best value because, damn it, you know. Okay, and then notice that it's the hydrogen spectrum that you're using, right? Okay, so use the lines for the hydrogen spectrum and not that for the deuterium spectrum, right? Okay, and then you're just going to plug that in. You're going to do two calculations, right? So for the red line, you're going to plug in, you're going to go n lambda is d sine theta, right? D is going to be this. Lambda is going to be the lambda for the red line, the big wavelength, right? 656.288. And then n will be, they say, the first order of the red, right? So put a 1 in there. Okay, and then for the violet, you're going to go n lambda. Oh, and then solve for theta. Theta equals something, right? And it's around 20. It's approximately 20 degrees, right? And then go n lambda equals d sine theta. We're going to solve for theta again here, right? Same d, right? Lambda is going to be your 410.180, right? Nanometers, right? It's going to be the second order, so put a 2 in there. And solve for this. This is going to be around 25 degrees. This will be around 20 degrees, okay? And then they want the angle that separates it, the angle between, right? Okay, so what's the, you're just going to subtract those. That minus that equals the angle, the difference in angle, right? Okay. And I got that one right, much to my surprise, right? Okay. And then they change it so that it's white light. Remember, it's a continuous spectrum. And we did this with our, when we looked outside. Remember, I had you guys look at white light with this, so we got the little rainbows. Okay. So notice that the center is white. Center is white light, just goes right through, right? Okay. And then you see the colored fringes on the outside like this, right? Notice that the orders, as you go out in orders, it spreads it out a little bit more, okay? First order, second order, there'd be a third order or something like that, right? If you could see that far to the side. The center is white, and then notice that it starts with blue and goes to red. And the reason for that is n lambda is d sine theta, right? The smaller the wavelength is, the smaller that angle is going to be that it diffracts, right? So it goes blue through red for all of those, okay? And that's what you need to say. All right.